Okay, does that work? Does this work?
Yeah,
You can hear me?
I think they view from the computer actually.
Oh, it's from the
Those
computer.
are fine.
But here in the room, I guess. Okay, anyway, hi everyone. I am going to talk about the influence of magnetic field complexity on stellar spin down evolution, and from early ages to later ages than typically I have done in the past. So sorry, this is not the summary, but the outline. I will discuss that there's an interplay first between magnetic activity and stellar rotation, and that there's a tension between Skuminich's law. Can we move this? Thanks. And rotation periods in stars. We recently know that it's not only in young stars. Okay. I will also discuss the role of magnetic field complexity in, whoops. So, doesn't matter. Okay. Oh, it's in there, yeah.
Yep. There.
Okay.
Rid of that first. What did I need to do, sorry? Yeah. Which one, the panel? Yes. Okay. Sorry, go ahead.
Okay, the outline full summary again. Yeah, so I'm going to talk about the role of magnetic field complexity in the rotation of young active partially convective stars, also fully convective stars, not necessarily so young, mid to late main sequence stars, and in other contexts, like binary stars. So let's start. This is going to be very obvious. Okay. For most of you, but I like to start from the beginning. Cool stars, when they rotate, they generate magnetic fields on their surfaces. These magnetic fields impulse magnetized winds. So rotation fuels activity through the dynamo action. And then these winds control rotation through magnetic braking. So this self-regulating mechanism by which faster rotating stars spin down faster as well results in a unique relationship between rotation periods and ages that depends on stellar mass or its proxy color. So this is the basis of gyrochronology. That is great because we can measure very well rotation periods and not so well ages. So that's why it's very interesting. And if we take constant age cats of this plot, then we should expect to see for coeval stars that the rotation periods of stars are a function of mass or color that evolves with age as the Skuminic law, the empirical Skuminic law that we have heard about a lot today. So period is proportional to time or age to the 1/2. However, when we look at rotation periods in young open clusters, I'm showing here rotation periods as a function of color for 6 different clusters of youngest cluster here to oldest cluster here. So keep in mind that fast rotators are at the bottom in this plot and low mass stars to the right. So we do see in red drawn here that what we should expect to see, that is the Skuminic branch. However, we also see a branch of fast rotators that gets less and less populated with age. And this gap in between that points to probably a fast transition between the two. Of course, Skuminic is an empirical law, but because you would imagine we can also get Skuminic from first principles, and we can. I'm not going to go through the math here, but you can look at Cowler in '88 paper that does this. So the main thing here is we use basic first principles, but we have to assume that the field here, this is the magnetic field, how it depends on R, depending on the main field of the star, meaning if it's a dipole, a quadrupole, or what order of field we have. We have to assume that that number is 1.5 to recover Skuminic. That means we have to assume, we are assuming when we use Skuminic, that the field is radial, it's somewhere in between radial and dipolar. Okay. But when we look at stars, I'm showing here planar projections of the stellar surface colored by the magnetic fields. when we look at this Zeeman Doppler imaging maps, we see that stars are not dipolar, or at least not always, or we could argue not most of the times they're not. So the question now is, what does this do to the angular momentum loss in stars, right? Because we are expecting them to follow a law that only works for dipolar stars, and they're not dipolar. Oh, sorry. So not only they're not dipolar, but we see a systematic change here. So we did the spherical harmonic decomposition back into 2018 of all the CDI maps that were available at that time. And we find that the dominant order in each of these, in a magnetogram decreases with rotation period. And I am going to explain in a little bit what I mean by this dominant order. It's just one number, but I'm going to talk about it in a little bit. So what does that do to the angular momentum loss? And can that explain the bimodal distribution or rotation periods? So to answer that question, we use MHD simulations, a non-ideal MHD code that is called AWESOME, that has been mentioned in many talks. That's the most realistic tool we have right now to model winds of stars, of cool stars. And we see that we do this many times for stars with fixed stellar parameters, fixed magnetic flux, and changing only the complexity of the field. So I'm showing here a dipole and quadrupole, octuple, and increasing complexity to the right. We did it for 10 orders, but I'm just showing 6. And I'm showing only the closed field lines, because if you look at the first one, the open field lines will make the plot very confusing. But you can see that the open field lines arise from where there's no closed field lines. What we see is this massive closing of otherwise open field lines as you increase complexity. And that leads to a very strong suppression of angular momentum loss as you increase complexity. Here, complexity increases to the right. This is the angular momentum loss efficiency. And so why does this matter? I want to point this out. We see here that the dipole is the order that dominates. And the higher orders, like from dipole to quadrupole, you lose an order of magnitude of angular momentum loss efficiency, and a total of 3 if you go complex enough. Why does this matter? Yeah, of course, higher orders do not contribute too much to the angular momentum loss. But it's exactly that is why it matters, because when you measure something, we heard enough today that you measure the total flux if you want to have something reliable. And so if the total flux is all in the dipolar mode, you'll get a very different answer in terms of spin down than if it is not. So any higher order here takes away from the dipole. And that is exactly why higher orders matter. They matter because if not, what is the alternative? You'll put all the flux in the dipole and you'll get a very different prescription for angular momentum loss. So anyway, with this scaling law that we did this for many simulations, we get a very clean dependency. We derive the most simple spin down model you can think of, which is Skumanich that we saw that is describing how a dipole evolves, times this complexity modulation. So the modulation of the distribution of the magnetic field on the star that we get from the MHD simulations. So that's exactly what we should expect. And then where do we get this end, the dominant order that I'm going to explain in a minute? We get it from that spherical harmonic decomposition I mentioned before. So from observations. Just doing that simple spin down model with one prescription gives us bimodal distributions of the rotation periods. So the blue is the model. You use one equation, you don't have to fit 2, and you get the bimodal distribution of the rotation period. And so bimodality naturally arises from this, is what we should expect. Then more recently, I want to tell you that, so here we're at the limit, very close, so we're at the limit of the fully convective boundary. And we see that our models shoot up and also adjust the data, as we saw today many times as well, right? And so we do see this abrupt change in stellar spin down near the fully convective limit that is consistent with what Lucy Liu described this morning in her talk, and we just saw from Federica as well. So we stopped here in 2018. We didn't go to fully convective stars because we thought that was a numerical issue of the convective turnover times that were diverging in that limit. But now we saw this morning also from Seth Gossage that what we thought was an issue here in the convective limit seems to be something physical. And so now we did go to fully convective stars, and I'm showing here same kind of thing, but now the x-axis is age, the y-axis is again rotation period, and we're doing this for different masses here, fully convective and then 0.4. Oh, we're almost there. Oops. Okay. Anyway, the main takeaway from here is you still get the same results. You get the bimodality here. Like if you look at any constant age, you can see that bimodality depends on the age of the star, as it does with of the mass of the star, where it happens. And that is consistent with Elizabeth Newton's observations of bimodality in the rotation periods of M dwarfs. And then, so let me tell you quickly, how do we apply, I promised to talk about that N. How do we apply this to real stars? Real stars are not pure modes. They have mixed modes, right? They are a combination of dipole, quadrupole, octupole, of course. And so we did this in 2016, where we took 8 observed magnetograms, including solar minimum and solar maximum. And the question is, the spherical harmonic decomposition cannot be described in one number, right? Because it's just more than that. But what we can do is take the most intuitive way to define what is the dominant order. And what we did was, okay, let's take the order L times the flux in that order. So a weighted average of the order divided the total magnetic flux. And let's see what happens. Let's see if it works. It's the most intuitive way you can do it. At least I thought so. So let me show you what happens. So we did that for all those magnetograms. And if we first calculated the total flux of each magnetogram, we ran it as an MHD simulation as if it was a dipole. So we put it in a dipole with that flux, and we get the triangles here. That is the angular momentum loss efficiency that we get. Then we use our scaling laws to go from that to what we should expect with that complexity of that particular map. We do this analytically. We calculate the complexity and we go down that line. And then we go to the different, to this other plot where we get those two. The hollow is the analytical and this one is the dipolar. And we run the MHD simulation with the observed map. And you see that it works very well. I mean, if you ignore the complexity, you would get here the triangle. But if you do the analytical thing, you'll get very close to what you would get if you do the full simulation. So it does work in real stars and with mixed modes. That's the main takeaway point here. What about M modes? Because I talked about L in the spherical harmonic decomposition. One thing is the order, and the other thing is M that is encoding the axis symmetry of the solution. You can have, for example, this is L5. So for this order, you can have all these different realizations of that order that have different axis symmetry. Zero.
Yeah, we're really out of time.
Okay, sorry. So I'm going to just tell you the highlights. That doesn't matter. Axis symmetry does not play any role. We run a lot of simulations. They really lie on top of each other. So you need to only worry about order. But I wanted to talk about stalling in later ages. Let me just tell you briefly that. Okay. Sorry, just let me tell you that the model also explains if you, so sorry, just to conclude, let me tell you that what was found more recently by many people, including Travis and Jen Van Saters and Ruth Angus, is that later later near the end of the main sequence, you get stalling, or so stars don't lose angular momentum as they should. And if you use this same idea and this same model, then you can explain that too. Also works in other contexts. I'm not going to talk about all this. Okay. Anyway, yeah, sorry. Any questions?
Yeah, what I propose is that people try to find your dinner.
Sounds great. Yeah, sounds great. Sorry.
We can move to the last part
Because we're really running late. And so we have Adriana that is coming to talk to us, and I'm going to find your presentation right here so we can.
Okay.